This is Lab 1 constant velocity in motion for Suchit's Monigati. For this lab, we will be observing an object moving at a constant velocity on a straight line. Um, we'll be trying to compare position as a function of time with two cases of position, one using experimental measured position using tracker, and then a computational predicted model using Python and Newton's second law. A brief summary of what happened after is the ball rolled at a constant velocity as a result of no net force, and both models were accurately able to depict what occurred during the actual experiment. So Newton's second law, basically, at its core, it's just the sum of the forces, the net force is equal to mass times acceleration, and then from there you can derive all sorts of equations. The first of which we'll be using is the velocity update formula, which is the velocity final is equal to velocity initial plus F net over m times delta t. For the purpose of this experiment, F net is 0, therefore the velocity stays the same throughout. The initial velocity came from the push of my fingers and no other push from there. We'll be using the position update formula as well, which is just the initial position plus velocity times time. We can use this because F net is equal to 0. And so, if I go to tracker, here is just a quick video of these are the frames that I analyzed, and as you can see, the position line is linear. On my screen I also show the glow script code, and the ball's mass is 0.26 kilograms. The velocity measured from tracker is it traveled 0.67 meters in the negative direction in 1 second, which is how I got the velocity vector. I used a while loop, and then the force net is the 0 vector. I input the velocity update and position update formulas from earlier, and then that's the Python code for that. The experiment setup, you can pause I actually explained all of this from the glowscript code, but if you need to, you can pause the video and see more about it. Here's a line graph comparing the tracker data and the glowscript data, and the blue is the tracker data and the red is the glowscript. And as you can see, they're fairly similar. They're very closely similar, with maybe some error in the tracker data due to having to click for each individual frame where the center of the ball is. I had to make assumptions for this experiment to actually work. I assume that there's no net force in the middle of the roll, that the only source of force that came was from the push of my fingers. I assume that the ball had a diameter of 0.21 meters due to it being a standard volleyball. I assume that it's traveled in a straight line with no curves. Curves would have altered the distance traveled, but a straight line would be perfect for the video analysis. And I also assumed that the tracker positions are accurately placed while clicking in the application. If we were to flip the axes, the ball would then travel in a positive x direction and thus have a positive velocity. However, the magnitude and distance traveled would remain the exact same. Only the velocity would change. There are mainly two attributable forces on the ball, the force of gravity pointing downwards and then the normal force from the table pointing upwards. They cancel out, resulting in a net force of 0 throughout that 60 frames, and as a result there's a constant velocity.